This is fundamental theorem. Asset pricing. If that the model is viable, if not, if it admits Q actually. This property will satisfy these conditions. One side is pretty easy. I mean, if the model is viable, then it, admittance of Q is going to be pretty much easy by just simply solving the system of solve the system of equation. Okay. This system of equation, for example, S naught I, and just take any spot S naught I and Qj S1j S1I of omega j, if j runs from 1 to n, and sum of Qj's is 1 to solve the system of equation. Okay. Viability is not a trouble. The real trouble is basically the converse. I have a differential probability measure. Okay. Then how you can show the viability of the model. So the real serious question is basically the converse equation. And you have this neutral probability measure which satisfies these two conditions. That is, it satisfies this basically Q of delta S1 bar is 0. Okay. We have this. How are we going to show that the model is viable? In other words, there is no risk into it. There is no arbitrage. We're going to focus on converse side. Do you really understand this basically? You want to show me an example actually, concrete example. Let's see a concrete example that what does this thing mean actually. The concrete example is, if you see the notes is this 3.4 example. Okay. Where the sketches where it takes basically model 3.3. Model 3.3 is a model with two stocks. Okay. And it's S mod 1 is, say for example, 100, and S mod 2 is 160. Okay. This one, the one is the one is 55. Interesting. And right. Like you can just see it from both ways. Just see it from both ways. You have those with you. You have PC with you, just open it and see that model. So what is actually, author is doing in this example 3.4 is that it is computing the value of delta S1 bar. So the model is given to you. Okay, model 3.3 from the rows. Right? You can see it from there. And it computes computes with basically what? It computes this delta S1 bar, the increments. And increments turns out to be, the increment is going to be vector actually. Okay. So the increments turns out to be, so it's like this is delta S1 1 and delta S1 2 actually. Okay, so delta S1 1 is what? Just like S1 1 minus S0 1. S1 2 minus S0 2. So you have these values from model. Just put them here and so it computes the values. I'm directly writing 100 and minus 110. Omega is omega 1 and it computes the value. The value is 40. These computations, if omega is 2, which I haven't wrote it, you can see for 1, computes 4090. If omega is 3, minus 40 and minus 40. Omega is omega 1 omega 2. 3 and omega is omega 4. It computes these increments. So model has been given to you to compute the increments. Then do what? Just plot these points. But plot where? On S1, S2 axis. Okay? On delta S1, delta S2 axis. Delta S1 1. Delta S1 2 axis. Okay? Can I plot them? It's easy. Okay, so when you plot them, you're going to have something like this. So it is 4090 roughly. So it's going to be this kind of, the points are going to be, one point is here, and another point is here, and one point is going to be here, and one point is going to be here. Do you think that heuristically this is an okay picture? So this must be which value? Which of these points?
4090.
It should be 4090. And this point
4040.
4040 roughly. And this point would be
100
minus 10. This point
minus 20 minus 20.
minus 40 minus 40. Now, what is the meaning of geometrically? What is the meaning of span of all these points, of all these vectors? What is the meaning of span?
Span vector space one there.
So, what?
Plane one.
What is the definition of a span of a? Okay, so one definition is the span of this basically. That the span by a set is the set of all linear combinations of. But there is another definition of it, or maybe definition or equivalent condition for the span actually. So the span generated by a set, just like if I have a span of some set, for example A, so then we're going to say that it is the smallest subspace
That is
That contains
that contains. It's the smallest subspace that contains. Okay. So if we want to interpret on this basically, picture what does it mean? We're going to say what is the smallest region which contains all these 4 points actually collected by these. So it's going to be roughly which region? This region. All that is basically what it was. In other words, I can achieve any of these points or vectors
And
by taking
Span.
some combination of these 4 points. Question. Does this convex combination contains origin?
sure.
it does.
So it contains origin. Pictorially I can see that.
So
It contains, so if it contains a region,
Viable.
it's a viable model. Okay. That was two dimensional. In 3 dimension, you're gonna have, so instead of plane, you're gonna have some, you know, convex region. Okay. You know, 3 dimensional region. Okay. A part of a space. You're gonna see that whether it contains 0 or not.
Origin.
So if it contains 0, it's viable. If it doesn't, it's not viable. So that's what we want to do. So there was one concrete example.
Sir, should
You
it
can
not?
see this example, the details of example from both.
Sir, should it not always contain 0?
Huh? That's what we're going to show, that basically if it contains, then the model is viable. If it doesn't contain, the model can't be viable, then there is going to be an arbitrage opportunity.
Spend the 0.
Okay? Okay, so you want to say that is it necessary? Alright, I can see your point. So span must always be a
Vector space.
subspace actually, so it should contain
0.
Okay. But if it is not containing 0, so it's not a subspace in the first place. So in other words, we are saying roughly that you have these increments. Okay. Do these increments form a subspace or not? Convex subspace. Their convex combinations form a subspace or not. If yes, the model is viable. If no, it's not viable. That's what pretty essence is. Obviously, if model is going to contain, say for example, more than 3 stocks, then it's not possible to draw it like that. You can draw it up to 3, but not go beyond 3 at least geometrically. You can do it beyond 3. So let me just give you a quick lemma, which is going to be sufficient for for the proof of first fundamental theorem of first pricing. So why learning theories in such a way is important? With every single detail, not leaving any gap. It's because that if you want to do research in this area, you need to have a bigger picture. But if there are some parts missing, you will always be stuck. My aim is that when we when you're done with all of the key contents in this basically discussion, then I must give you a paper as well, so that you can see that okay, what we have done is not something of no use. People are still working on it and doing something substantially important. Okay. So here's a lemma. Here's a lemma. So this actually in a single period model with M stocks and scenarios. Following a recovery. there is risk neutral probability. Number 2. Zero belongs to the This is the reason that he's not using in this book, the author of this book is not using the word span actually. Because for a span there must be zero inside it. Using convex hull, which is just simply the set of all possible combinations of the vectors, which does not necessarily contain zero. So you can say, okay, there is a difference between both.
Okay.
So that will be one of the issues. Like convex hull is a set of all possible linear combinations of given vectors. So if it contains zero, then it's a span. Okay. If it doesn't, shouldn't say span. Now obviously zero is going to be in the span. Zero belongs to what? Zero is in interior of convex hull